Hello everyone. This is related to entropy. So we have two things: 10 kg of water at 300 Kelvin and 10 kg of water at 350 Kelvin, and we are mixing them, and heat capacity is same for both. So this is very standard problem we can solve, and we have to calculate the entropy. Okay, entropy generation in this mixing. Okay, so let's say we have like this A and B, and this is insulated, like, because neglecting any heat losses to the surrounding. So our system is this, and surrounding is this is the system. Okay, so here we have 10 kg of water, 3 Kelvin, 300 Kelvin here. So we'll call it as MATA, and this is MBTB, and both has C. So MA is equal to MB equal to, let's say, M, and CA is equal to CB is equal to C, and TA is not equal to TB. Okay, these are two different things. So after final mixing, what will happen? They will come to some uh, final temperature. So using first law here, if we apply first law, del Q is equal to du plus delta W. No heat loss to the surrounding, no work done, as no shaft is given, no electrical work done, no piston displacement work done, as well as volume is rigid. So du is equal to 0. So internal energy change of side A to internal energy change of side B. So let after mixing, some final temperature is achieved. So for this part, M MA equal to MB equal to M. That's why I'm using M. Let's say MA. Okay, let it be like this. MC dt. dt is T final minus T initial. T initial is, let's say, Ti. Let's say TA. TA means T initial. MACA plus MBCV T final minus T initial means initial temperature is TB. Let's say. Okay. So if we solve this, so TF will be equal to MA. We can write MACCA equal to MBCV equal to MC. Okay, because for uh, mass of water is given same, and C is also same. So we can write it like this. It will become MCTA plus MCTV divided by MC plus MC. So if we cancel the term MC, we will get TA plus TB by 2. So the final temperature will be how much? Final temperature will be 300 plus 350 divided by 2. This is 325 Kelvin. This is very easy. Now, where we have calculated final temperature, one can ask this question. Why? Because this we have been given liquid. For liquids and solid, we calculate enthalpy using TDS relation. TDS is equal to du plus PdV, means CVdT plus PdV. Okay, and TDS is equal to dH minus VdP, CPdT minus VdP. Now see, so which equation is used? This is for ideal gas. For liquids, we directly use ds is equal to C ln T2 by T1. Okay, so that's why we know the initial temperature, but we don't know the final temperature after mixing. So that's why we have calculated the final temperature. So now what I can do, I can calculate the entropy change of the system by using just formula for side A and side B. So we, if I calculate for side A, let's say this is our main equation: delta S total equal to delta S of system plus delta S of surrounding. So surrounding is 0, no heat transfer to the surrounding. delta S of A plus delta S of B. So delta S is equal to delta S of A will become MACA is equal to ln of T final divided by TA, and for B also MBCB ln of T final by TB. Okay. Now what is MC? MC we can take common. So this will be ln of TF into TF divided by TA into TA, TB. We can directly write MC ln of TF square divided by TA TB. So delta S will be 2MC ln of TF divided by TA into TB. So delta S will be 210 to 4.2 into ln of 325 divided by 300 into 350. After calculating, you will get delta S is equal to nearly around 0.25 kilojoule. Okay, so we have directly calculated M, so it will come out to be kilojoule in kilojoule. Okay, so here we have been asked to calculate the slope of isothermal curve for a finite volume system containing an ideal gas. In this scenario, here Helmholtz function is on y-axis and space volume on x-axis. So what is the expression of f is equal to f is equal to u minus ts, right? So if we take d of both sides differentiation, so it will give tds minus sdt. So TDS using TDS relation. Why? Because here no volume term is appearing. So, but in TDS relation we can get volume term using this. So if I write minus TDS is du plus PdV minus SDT. So this du will get cancelled. df is equal to minus PdV minus SDT. So for isothermal curves, temperature equal to constant. So df is equal to minus PdV. So del F by del V at constant temperature is equal to minus P. So note that this P is absolute, absolute pressure. So this cannot be negative or zero. So therefore it is always positive. This is always finite, non-zero, non-zero and negative. Why negative? Absolute pressure is always positive but negative sign is there. So that's why. So finite, negative and non-zero C is there. So in question number 11 also we have been asked the same question, like there were four questions were there. See, here already in this question we have been asked this first and second problem. So this was combined question. If you are able to solve this question, you will also solve that. So here we have given two cycles, cycle M and cycle N, and some questions are have been asked. Some options are there regarding efficiency, heat rejection, net heat transfer, and heat input. So uh, this is a cycle. So for a cycle, the first law we can write as first law simply is du plus delta w. So these are path functions. This is a state function. So in a cycle, when we start from A and comes back to A, okay, or when we start from D comes back to D, so this will become 0. So for a cycle, delta Q is equal to delta W. Whatever the net heat transfer is there, that is equal to net work transfer. So this is PV diagram. Okay, so area under the curve will give net heat transfer, and that will be equal to net work transfer also. Okay, so if I try to calculate area under this curve, cycle M. So delta W of M, this will equal to, this is triangle, half base into height. Base is uh, 2V1 minus V1 and height is 2P1 minus P1. This is simply half V1 P1. And if I calculate the work for cycle N, so similarly same here also, 2V1 minus V1 will be 1 and this is also 2P1 minus so we can say delta W of M is equal to delta W of N. So since therefore delta Q of M, net heat transfer in cycle N is equal to the net heat transfer in cycle M and N are same, using first law of thermodynamics for a cycle. This question is related to psychometry. So here we have given state 1. So in this condition of moist air, we have 100 moles and relative humidity is, see, 100 moles of moist air, relative humidity of 70% means 0.7. Okay, and temperature is given 70 degrees Celsius. This is 343 Kelvin. And at second state, the temperature is 50 degrees Celsius. So in the table, whatever has been given, it is not the vapor pressure directly, it is the saturation vapor pressure. So whenever you have been given any data with respect to temperature, it is the saturation pressure, not the vapor pressure. They will not directly give you the vapor pressure. Okay, so saturation at 1 will be 31.16 kilopascal and P sat at 2 will be what it is, 12.34 kilopascal. Now note that here it is cooled from this to this at constant pressure of 1 bar. If we are cooling anything, let's say piston cylinder arrangement, if we are cooling thing, temperature is decreasing, so volume will also decrease. Using ideal gas equation, if we see, if temperature is uh, constant, like pressure is constant and temperature is decreasing, volume should also decrease, and the mixture of dry air and water vapor is moist air, so it already follows the ideal gas equation. So it will it will be the volume will decrease. So we don't have any information about the volume at 1 and 2, but we only know that V1 is not equal to V2. And also note that the composition of dry air in the moist air will be constant. Okay, what changes is the water vapor content. Okay, it only differs. So at 1, what we can calculate, so we are asked to find out the number of moles of water vapor left in the moist air. Okay, so let's calculate the number of moles in initial condition, first condition, then compare it with second condition. So we know the total pressure is how much, air का pressure plus water vapor का pressure. Then we know total is 100, 1 bar na, 100 kilopascal. P of air at 1, P of water vapor, and water vapor we know how much. We have to consider how we can calculate water vapor ka pressure at 1 using P of V at 1 is equal to phi at 1 into P saturation at 1, right? 0.7 into P saturation, it is 31.16. It is coming out to 21.812. Nice. So 21.812. So air cup pressure will be equal to 78.182 kilopascal. Now we have ideal gas equation for this. So what we can do, if we try to calculate the number of moles of like water vapor and air, we can calculate how P of total at 1 into V1 is equal to N total at 1 that we know into R bar into T1. This is first. Similarly, PA1 is equal to Na1 number of moles of air at 1. Then this is second, and PV at 1 into V1 is equal to NV1 into R bar into T1 is equal to 3. Now, if I divide 1 by 2, that will be equal to P total at 1 divided by PA1 into N total divided by Na1. Okay, right. So Na1 will be equal to N total into PA1 by P total. So that will be equal to 100 into 78.182 divided by 100. So number of moles will be equal to this this many moles of dry air we have in first condition. And number of moles of this vapor will be equal to total is 100 minus, if we subtract this, so this will be 21.812 moles of water vapor initially what we have. Okay, and let's understand the situation in 2. So at 2, what is happening? So our PV1 is in first case is 21.812 kilopascal, but P saturation in the second case is 12.34 kilopascal. Okay, so the saturation pressure in state 2 is itself lower than the vapor pressure at state 1. So condensation will take place, and that PV2 will be equal to P saturation at 2. So by this we know the vapor pressure at second stage. Okay, now at second stage also P total we know 1 bar only. At constant pressure condensation will happen. So Pa2 plus Pv2. So here Pa2 will get 100 minus 12.34. This is equal to 87.66 kilopascal. So what I have told you that that the dry air number of moles of dry air will be equal always. Okay, it will not increase decrease. What will increase decrease is the number of moles of water vapor. So Na1 equal to Na2. So what we can use now, if we write the ideal gas equation for dry air and water vapor, it is state 2. What will get? See, Pa2 V2 is equal to Na2 into R bar T2, and PV2 into V2 equal to NV2 into R bar T2. So 3, 4, let's say. So 3 by 4 if I do, so Pa2 divided by PV2 equal to Na2 divided by NV2. So NV2 is equal to Na2 into PV2 divided by Pa2. Right? So this is equal to 78.182 into 12.34 divided by 87.50. So NV2 equal to 11.00577 moles. So number of moles of water vapor in the second stage will be equal to 11 moles. So this was some doubtful question, but it was like moderate level question, moderate to difficulty or something. So this is question from Carnot engine. So this is very good question because efficiency of Carnot cycle is given by 1 minus T2 by T1. Okay, so here T2 is sink temperature and T1 is source temperature. Okay, now see that uh, increasing this and decreasing this both increases the efficiency, but in the question it has been asked which one of these cases, in which of these cases efficiency will increase the most. So some options are there: increasing T1 by delta T, increasing while other keeping constant. Okay, so let's try both. So if we try efficiency 1, let's say by TH plus delta T, we TS को delta T से increase किया, then what is the efficiency? Okay, so TH means T1 को increase किया, 1 minus T2 by T1 plus delta T. Okay, so what will that become? T1 plus delta T minus T2 divided by T1 plus delta T. Okay, now let's see second case where we are reducing the sink temperature. So that will become efficiency at 2, 1 minus T2 plus delta T. Sorry, T2 minus delta T, because we are reducing something, no? So T2 minus delta T, but delta T is same both in both the cases. If I take the LCM, T1 minus T2 plus delta T divided by T1. So note that numerator is same in both the case, but denominator is different. So here denominator is higher, so efficiency will be less, right? Denominator in case of eta 1, efficiency in first case is higher, so that the whole value will decrease, but here only T1 is there. So efficiency in case 1 is less than 2, means decreasing the temperature, that sink temperature by delta T will increase the efficiency most. So there is another approach also. So we have got our answer T2 by delta T while keeping T1 constant, this one. But whenever it is asked which way it will be most, so we can go for differentiation. So efficiency is equal to 1 minus TL by TH, right? If I do the efficiency uh, by with respect to both, like the total enthalpy change, so if I do the maths here with respect to TL, lower temperature reservoir, this will be 0 minus 1 by TH and minus 1 by TH, and efficiency with respect to DTH is equal to so this will be 0 minus TL will be constant, and differentiation of 1 by TH will be minus 1 by TH square. Okay, so this will be positive TL by TH square. So here you can note that what we have done. So we are simply seeing the total change in efficiency with respect to temperature change. Okay, with respect to TH and TL. So this will be due to both. Okay, so whoever has the highest slope will have the most effect on the efficiency. So it is coming out to be negative. See, the efficiency divided by TL is, it is coming out to be negative. If the slope of this is larger than this, so decreasing TL will increase the efficiency most. If the slope of this process is larger than this, so increasing the higher temperature reservoir will increase the efficiency most, hypothetically. Okay, so let's see. So d eta by dTL equal to minus 1 by TH. What does minus sign indicate here? We are decreasing the temperature, like lower temperature reservoir temperature. Okay, And what does this indicate? TH. This is indicating 1 by, I am writing it like this, TL by TH. Okay, now see. So which process has larger slope? So just neglect the sign. See the magnitude. 1 by TH, 1 by TH common is common here. Okay, in both the cases. But TH is greater than TL. Okay, so this quantity will be less than 1. TL cannot be greater than TH. So efficient. So you can see that the slope of this is less than this. So this is most effective hypothetically. So decreasing T sink will increase the efficiency most. Efficiency most. So this is our question number 18. So this is nice question. So you have to pay attention here to this term steady flow process. For a steady flow process, work done is given by minus integral of minus VdP. So this formula you have to use. Otherwise, you will use the area under the work done because P you can easily calculate using volume, and once you know P and V, you will calculate the area under the work done, which will be wrong. So this process is coming out to be like this when you use area under the work done concept. But here it is clearly mentioned that it is a steady flow process. So we have to use this formula. So let's find out the pressures at different points. So we have for process 1 to 2, 800 V equal to 900. So using P1 plus 800 V1 equal to 900, it will give V1 is 0.5, so that will make it 400. 900 minus 400, it is 500 kilopascal. Similarly, P2 V2 P2 800 V2 900, because for process 1 to 1 1 to 2 we have this formula, so we can write P1 V1 and P2 V2. Okay, so here it is 1, so 900 minus 800, it will be equal to 100. Also P3 by P2 is 4, so P3 will be 400 kilopascal, right? And here volume is V1 is 0.5 meter cube per kg, and V2 and V3 is 1 meter cube per kg. Now see how you have to calculate. Total work done will be equal to work done in 1 say to 2 to 3. So integration of minus VdP from 1 to 2 plus minus VdP for which process? 2 to 3. Now see, here you can write V as for 1 to 2, V will be equal to 900 minus P divided by 800. Okay, so we will place use V here as 900 minus P divided by 800, right? So you should know integration. This will be equal to minus, plus and minus will make minus. Okay, 2 to 3, and V here is constant. Okay, it is not a function of volume, so we can directly take it out of integration and use dp here, right? So first term will become C. This is purely integration maths now. Here dp dp integration of dp. Okay, 1 to 2. If I take negative inside, so what it will make? Minus and plus here, so it will be 9 by 8 integration of pdp, right? And this will be P3 minus P2. Here I have integrated into V. Okay, now see, W will be equal to minus 9 by 8 P2 minus P1 plus 9 by 8 P square, sorry, 9 by it will not be equal to 9. This will be equal to 1 by 800, right? 1 by 800 coefficient of minus p. So this will be minus 1 by 800 into p square by 2, integration from 1 to 2. Let's put the values here. V is 1, P3 is 400 minus second is 100, right? Minus 9 by 8, P2 is 100 minus 1 is 500 plus 800 into 2. P1, it will make it as P2 square minus P1 square, right? P2 square minus P1 square. We can write it like P2 plus P1 and P2 minus P1. Okay, so P2 plus P1 is C. I will write this point. P2 plus P1, P2 minus P1 minus 300. Okay, so this will be equal to 400 by 8 into 9 plus 800 into 2, and P2 as P1 is 500. P2 minus P1 is minus 400 minus 300. Now see, this is 2 and this will be 4. So this is 450. This is I think there is some mistake. P1, we should know P1 and P2. 500 and 100. When we add them, 500 and 100, that will be 600. Okay, this is incorrect. So 400 cancels 800. So 2. So 600 by 2. Don't miss negative sign. 600 by 4. Okay, this will be minus 150. And here minus 300. So this will be 450 minus 450. It is equal to 0. So only catch here is this steady flow process. So work done for a steady flow process is given by this relation. Okay, thank you.